All right, Chemistry 3111. We left off with this question, 21.25 C, and then we also said we were going to take a look at 21.26 B. Okay, these two reactions. So these are Claisen reactions, so Claisen condensations. And what the mantra I was trying to give you last Friday was if it's a Claisen reaction, it's a beta keto ester that you're going to end up with. So if you see a beta keto ester in a synthesis and you want to make it, right, you would make it from a Claisen reaction. So if we're starting it with this ester and we're treating it with ethoxide as our anion, right, we're going to form the anion. So I'll just draw the anion, excuse me, here like this. All right, like that and like that. Okay, so we have both of these species in equilibrium, right? We've got some of the un, uh, the neutral form, and then we have some of the enolate. And as I drew before, right, this is our alpha. We can think of this as being our alpha carbon, and we have a nucleophilic attack onto our carbonyl like this. And of course, I'm not going to draw the complete mechanism, but you can see where the bonds are being connected, right? So if that's my alpha carbon, then this is going to be where my beta ketone is. Excuse me. So to draw the final product, and again, we're not asked to draw the whole mechanism, what we're going to do is we're going to start it with the skeleton that they gave us. Okay, so we're going to draw the ester here. Okay, now keep in mind, this is our alpha carbon, so beta is where our carbonyl is going to be. And then all we have to do is draw all the rest of this like that. So I'm just going to twist it up in this direction just so I don't run out of space, but we end up with something that looks like that. So there you go. So there's our beta keto ester, right? And again, just to repeat myself like an old person, this is your ester, alpha carbon, beta carbon, and on the beta carbon you have a ketone. So a beta keto ester. All right, so that's the product of that Claisen condensation. The next one, they give you the products of a crossed Claisen. So both of these require two different esters, but you're just asked to tell, what are the reaction conditions. And we did the first one last week, and we said, okay, well, the starting materials are going to be this ester, right, which I have drawn here. You're going to treat that with LDA, and then the other ester is going to come from this portion here, okay? And that's what I put over here. The only difference is I added the OET group, right? Because it's an ester. So we're going to do the same treatment here. So you see that we're actually starting out with the exact same ester, which is ethyl propionate that we used in the last one, okay? So we're going to start with our ethyl prop. That's not a very good drawing. So we're going to start out with our ethyl propionate, which looks like this. Which looks like this. In step one, we're going to hit it with LDA. In step two, we're going to treat it with our other ester. And so if I just circle this part in green, you can see what the ester is going to be. So let's pencil that in. It's going to look like this. And then, of course, we want to use ethoxide, right? You have to use ethoxide in this case to avoid transesterification. And then the last step is going to be aqueous acid, and that is going to give us our product. And again, if you want to go back and review this is what we call a crossed Claisen, right? Because we're using two different esters to make the beta keto ester in the end. All right, there you go. So that's just a little review on Claisen reactions. Then after that, we looked at alkylation. So we looked at kinetic and thermodynamic enolates, and that was kind of covered here. So we said if we want to do a kinetic enolate, we use sodium hydride at room temperature. A thermodynamic enolate, we use sodium hydride at room temperature. If we want to do a kinetic enolate, we use LDA at minus 78 degrees Celsius. And I explained why we use a weird number like negative 78 instead of negative 80. It's because when you mix dry ice and isopropanol, it makes a bath, which is minus 78. So we went over these, and students were really good at those. And so that brings us to the next new topic, which is the malonic ester synthesis. So I'm doing them in the reverse order from the textbook. So in the textbook, he does the acetoacetic ester synthesis first, meaning you scroll down, he does this one first. But anyhow, I'll just do them in reverse order because that's the way they were taught to me. But anyhow, we're just going to go over all the content anyway. So the first new transformation that we're going to do today is to take an alkyl halide. So you guys know what an alkyl halide is by now. And of course, X could be any leaving group, but we're going to use halogens. And then you're converting that into a carboxylic acid, but you're adding two new carbons. Look, you're adding carbon 1 and 2, and the second carbon is the one that has the carboxyl group on it. So a pretty neat reaction if you think about it. If you think about acetic acid, which is this acid, right? This is acetic acid. It's the acid that's found in vinegar, so acetic acid. If you think about it, it's almost like sticking acetic acid on the end of your R group, really, is what you're doing, okay? So that's one way to kind of think about it, if that helps you digest the content. But anyhow, how do you do this neat reaction? Well, you actually have to have a starting material called diethylmalonate, okay? So diethylmalonate, the structure is shown right here, so you're going to have to practice drawing the structure, which looks like this. If you guys remember, oh my stars, go away. So oh my, so my was malonic acid, which has 3 carbons. So this is diethylmalonate. So it's just the diethyl ester of malonic acid. So this is diethylmalonate, this compound here, and it's actually not over the reaction arrow. It would actually be over here somewhere. But anyhow, diethylmalonate, the first thing you do is you treat that with ethoxide, and that converts it to the stabilized enolate. And you guys know that you could have the negative charge here, here, or here, depending on whichever resonance form that you draw. So this stabilized enolate is now going to function as a nucleophile. So what we're going to see is we're going to convert it into the enolate, and then it's going to do an SN2 on our alkyl halide. So let's take a look. So the enolate is then reacted with the alkyl halide. So you might be saying, now, what's the point of all this? Well, the point of all this is that now you have this diester. And what's cool about that is if you hydrolyze it, you hydrolyze this ester to a carboxylic acid and this ester to a carboxylic acid. And it turns out that this compound, like this, is actually unstable. Okay, so this here is unstable, and it rearranges and it loses carbon dioxide in the process. So it undergoes what's called a decarboxylation reaction. It says it's decarboxylated. But the bottom line is when it's decarboxylated, you're losing carbon dioxide. So carbon dioxide is a gas, so that's going to go up the smokestack or up into the air. So this is an irreversible reaction. And what have you done? Overall, you've added 2 carbons with a carboxyl group on the end. Now, the mechanism for the decarboxylation is shown here. I'm not going to write will not ask, but I've never asked this mechanism for any, in any of my quizzes or anything like that. But anyhow, it's a pretty cool mechanism. You can see it's a concerted process. It happens all in one step, 3 curved arrows at the same time. But then you end up with an enol. Now, the textbook calls this an enol. I think that technically you could call it an enediol because it's got 2 hydroxyl groups, but whatever. It then undergoes tautomerization to give you the carboxylic acid. Now that's a lot of information that I just fed you. So if you're wondering, like, what's the overall process, Mr. Dion? Here's the overall process. Okay, it's actually not that bad, I don't think. You start out with diethylmalonate. Okay, this compound here. You treat it with sodium ethoxide. It gives you the conjugate base. So then the conjugate base is going to do the SN2 on your alkyl halide. Okay. Then after you do that, you heat it up with acid, and that causes the decarboxylation reaction to occur. And so you end up with what? You end up adding 2 carbons on the end of your alkyl halide like that. Now, if you're a student, I know you all are, you probably noticed, well, hey, Mr. Dion, there's not 1 acidic proton here. There's 2 acidic protons. Couldn't I do a dialkylation, right, and make something like this where I have my 2 carbons here, right, 1, 2, like that? Absolutely. You can absolutely do that. And as far as the deprotonation and the alkylation is concerned, you can do whichever one you want first. So I'm going to put here order not important. And when I say order not important, I mean which RX you put in first. Okay, you can put in an ethyl group first and then a methyl group second, or methyl group first, ethyl group, whatever, doesn't matter. Just pick whichever one you want. Okay, so let's say you were asked a question like this one on a quiz, and it says, okay, what would your starting material be, or how would you do a malonic ester synthesis, okay, for this to make these compounds. So here's how I would do it. I would first of all say I need diethylmalonate to do a malonic ester synthesis. So I would recall what the structure of diethylmalonate is. Okay, so you have to have that kind of memorized. And then I'd say, okay, 1, 2 carbons. I know that this part of my molecule, this part is going to come from diethylmalonate. Okay, the rest of it, all of this is going to come from my alkyl halide. So I'm going to start by writing down my diethylmalonate, which looks like this, like that. Okay, and then I'm going to hit that with sodium ethoxide. Then I'm going to hit that with my alkyl halide. So what's my alkyl halide going to look like? It's got the 5-membered ring, then a methylene, right? CH2, make that prettier. CH2, and then you can put whatever halogen you want. You can put iodine, bromine, chlorine, I don't care. Okay, so we'll just use the chloride for a change. And then in the last step, you're going to treat that with hydronium. Now, we can draw, let's draw the intermediate after this step just for practice, okay? So what your intermediate is going to look like is this. So you're going to have your diethylmalonate molecule like this, but now you're going to have CH2 and you're going to have your 5-membered ring attached like that. So then all you have to do to finish it up is say, okay, I'm going to H3O plus and heat, and that is going to give me the product like that. Give me a thumbs up if you follow me on that. I think the hard part is remembering the structure of diethylmalonate and also the name, the malonic ester synthesis is kind of a funny name. But anyhow, let's try the next one. We'll do the exact same kind of approach, okay? Exact same thing. So the portion that's going to come from our diethylmalonate is going to be carbons 1 and 2 here. So we'll put a circle around all that. And that means that our 2 alkyl halides in this case are going to come from here. That's going to be one of them. And the other one is going to come from here. So you see that one has an ethyl group and the other one is an isobutyl group. Okay, so to draw out our synthesis, we're going to start with diethylmalonate. So there's my diethylmalonate. Then in step 1, sodium ethoxide. You can put whichever one of those R groups you want in. Okay, you can put the ethyl group first. You can put the isobutyl group. It doesn't matter. I'm going to put the ethyl group first. So I'm going to use ethyl iodide like that. So that's going to install the ethyl group. Then we're going to hit it with sodium ethoxide again. And then we're going to put in the isopropyl group, or sorry, the isobutyl group, which is going to look like this. So I'll use isobutyl iodide. That is going to give me what? So let's draw it out. So we're going to have our diethylmalonate. We've replaced both of those protons. We replaced one of them with an ethyl group, and we replaced the other one with an isobutyl group. And so to finish it up, we take it and we heat it with aqueous acid, so H3O plus, and heat, and we end up with the product. Just like that. And there you have it, folks. All right, give me a thumbs up if you think you could do that. Even if you're saying I have to practice it for 20 minutes, but then I'll get the hang of it. Great. So the malonic ester synthesis. It's something that you might not want to think about, or maybe you do. It depends on your interest level in synthesis. But again, if you go back to the beginning, think about what you do here. You're taking an alkyl halide. Alkyl halides are cheap, abundant. Okay, you can buy them all over the place. And then just using diethylmalonate, which is also a pretty inexpensive compound, you're able to make a carboxylic acid, and you add 2 carbons. Pretty cool transformation, because once you have a carboxylic acid, what are you thinking? I don't know. I was thinking about chapter 20. There's so many different things you can do with carboxylic acid, right? It's almost like the sky's the limit in a way. So malonic ester synthesis is pretty cool. So let me show you the next one, which is acetoacetic ester synthesis. And again, I do them in the reverse order of the textbook, but the acetoacetic ester synthesis uses something called ethyl acetoacetate. So that's this compound shown here as your starting material. Just give me 1 second. And as far as the name goes, okay, so let me write this down here. So let me use my pen. So it's ethyl acetoacetate. Okay, So if you think about it, an ethyl group is this, okay? So that's an ethyl group. An aceto group is this, okay? And then if you think about what acetate is this ion here, okay? It's like this, okay? So you see how all those pieces go together. You have the ethyl, then you have the aceto, and then you have, then you have like the acetate and then the aceto group, but it's called ethyl acetoacetate. But hopefully that helps you. Maybe it doesn't. If you're just thinking, hey, isn't it like diethylmalonate? So if you were to draw diethylmalonate like this, okay, which you probably just practiced drawing, and then if you just remove the OET like that, there you go. That's what the compound is, okay? So maybe that'll help you in drawing it. So now what you're going to do with the ethyl acetoacetate is you're going to take your alkyl halide and you're going to add 2 carbons. Not 2 carbons. You're going to add one. Yeah, you're going to add 2 carbons. 1, 2. Sorry, I'm just trying to count here. But you end up making a methyl ketone on the end like that. All right. So it's actually, sorry, I'm still doing it wrong. It's 3 carbons. Let me see how you would draw this. 1, 2, 3. I guess like that. Okay. So you end up adding a total of 1, 2, 3 carbons, and you make a methyl ketone. So these carbons come from the ethyl acetoacetate, okay? And the rest of it comes from your alkyl halide. And it's the exact same reagents as the malonic ester synthesis. It's identical. So first step is to treat it with sodium methoxide. You make the doubly stabilized enolate. That's a nucleophile. This is an electrophile. Then you heat it up with acid and you end up doing a decarboxylation reaction again. Okay, so you end up with an enol and it tautomerizes to give you the methyl ketone. Now, I'm not going to ask you to draw the mechanism of it. So let's say you wanted to synthesize these compounds doing the acetoacetic ester synthesis. Here's how I would do it. I would count 1, 2, 3 carbons from the end. That's going to come from your ethyl acetoacetate. That means that all the rest is going to come from your alkyl halide. So what are you going to draw? You're going to start by drawing ethyl acetoacetate, which just looks like this. Okay, step 1, sodium methoxide. Step 2, your alkyl halide, which is going to be this compound. So we have, I'll just use the iodide, okay, and I'll even color code it here. So we'll turn it to blue like that. Okay, and then what are we going to end up with? We're going to end up with something that looks like this. So we have our ethyl acetoacetate like that. Now we're going to have our alkyl halide like that. And then to finish it off, we're going to do H3O plus and heat, and that is going to give us the final product. All right. So for the next one, again, the exact same vein. We count 1, 2, 3. So we're going to need 2 alkyl halides. We're going to need this one. And then we're also going to need this one. So one's ethyl iodide. The other one we'll use benzyl bromide or something like that. So again, same strategy. We use our ethyl acetoacetate, which looks like this. Sodium ethoxide. I'll do both. So then in step 2, we're going to use this compound. This is called benzyl bromide. Okay, you could use the chloride if you want. I don't care. It doesn't matter. Then in the next step, we're going to hit it with sodium ethoxide again. Then we're going to use ethyl iodide. And if you used ethyl bromide or ethyl chloride, that's totally fine. Like that. That's going to give us this compound. So we have our ethyl acetoacetate. And we have our ethyl group, which is in red. So I'll put that over here. Like that. And then we have our benzyl group, so CH2, and then our aromatic ring. I'll just put pH for the aromatic ring. And then to wrap it up, cook it up with some acid, heat, and then you end up with some sweet, sweet product, just like that. There you go, my friends. So acetoacetic ester synthesis and the malonic ester synthesis. Okay, if you go to the very end of the chapter, where he gives you kind of a summary of all the different things that we covered. So last class, we finished up to this point. We stopped here. And today we're kind of starting here. So this is kind of June. So today, so we've covered these two reactions, malonic ester synthesis and acetoacetic ester synthesis. Both of them pretty cool syntheses that enable you to make a carboxylic acid. When you make the carboxylic acid, you add a total of 2 carbons. When you make the methyl ketone, you add a total of what? Come on, slides. 1, 2, 3 carbons. Give me a thumbs up if you're with me on those two syntheses. Everybody with me on those ideas? Kind of a new way of, or just a neat way to make a carboxylic acid. And then we also looked at a way to make a ketone. All right, so what we're going to cover today, we're going to spend most of our time on this stabilized carbon nucleophiles, which leads us into the storic enamine synthesis. And then the Robinson annulation is just 2 reactions that we will have covered by the time we get there. So it's actually going to be a Michael addition followed by an aldol condensation. So Robinson annulation, I'll even put it in here. So it's a Michael addition or Michael reaction followed by aldol condensation, which we covered in detail earlier on. All right, so let's go back and let's get into what we call the Michael addition or the conjugate addition reaction. So let me find it. Where was it? It was over here somewhere. And you're going to have to kind of be on your toes a little bit through the conjugate addition reactions, but it's pretty cool chemistry in terms of making new molecules that you might not have thought about before. So let's start. So it says, if you have an alpha beta unsaturated carbonyl, how do you make that? You make that via an aldol condensation. And we went over aldol condensation and aldol addition in detail, right? The difference with aldol condensation is that we use sodium hydroxide and what? Heat, right? Because we drove water out of the molecule. So if you take a look, so what we're going to do right now is we're just going to take some time and focus on this kind of compound, this alpha beta unsaturated aldehyde in this case, or it could be an alpha beta unsaturated ketone. But if you have this alpha beta unsaturated carbonyl, and remember, when we talk about a carbonyl, it means aldehyde or ketone. There's nobody who's listening to the sound of my voice who couldn't draw all 3 of these resonance contributors in their sleep. Okay, I know all of you are very capable of it. But if you look at these 3 resonance contributors, what do you notice? Okay, what they want you to notice is this, is that in the first one, you see how the carbonyl carbon, I feel like I can't see. Anyway, you see how the first one, the carbonyl carbon is electrophilic. But if you look at this resonance structure here, what do you see? You see a positive charge on the beta carbon. So look very carefully. This is alpha, this is beta carbon. So not only is the carbonyl carbon electrophilic, but you guys know that. We've looked at so many Grignard reactions. But now the beta carbon is also electrophilic. So let's write in here, electrophilic. All right, so what's the big deal? Well, check it out, okay? Is now either carbon can be attacked. You see both of these carbons, they have the delta pluses. That's the beta carbon, and this is the carbonyl carbon. Depending on the type of nucleophile, you can attack either one. So you can literally go to the cupboard and kind of choose your nucleophile. And to give you an example, if you chose like a Grignard, and you guys know Grignard's inside out, right? A Grignard would attack the carbonyl carbon, but for the beta carbon, let's say you pick the cuprate. You guys remember the cuprate, the lithium dialkyl cuprate? A cuprate will attack the beta carbon. So now you can do a nucleophilic attack at either position. This is kind of interesting, okay? And so if we add at the carbonyl carbon, right, using something like a Grignard, okay, that's nothing new to us. This is something we've seen many, many times this semester, okay? That's called 1-2 addition. Now, why do you think it's called 1-2 addition? I bet you know, right? If I look at atoms 1 and 2, the carbon and the oxygen of the carbonyl, well, on atom 1, I add the R group, and on atom 2, I add the hydrogen. So we call it 1-2 addition. However, if you do, if you add at the beta carbon, okay, and again, this is the beta carbon here, we call that 1-4 addition. Now, if you're looking at this product here and you're saying, no, it's not, because you added a proton here, so why isn't that called 1-2 addition? Well, it's a good point, okay? And again, this is a Gilman reagent or a cuprate. Okay, well, it turns out that when you do the addition, the hydrogen actually ends up on the oxygen to make an enol, but then that enol tautomerizes to give you the aldehyde. So that's why it's called conjugate addition. You don't believe me? Take a look, okay? So here's the mechanism of conjugate addition. I don't think I've ever asked students to draw this in gory detail or anything, but I do believe, I'm a firm believer that this is a very important mechanism for somebody at this. I mean, you guys have studied a lot of organic chemistry at this point. So how does conjugate addition work? What you're going to do is you're going to get a nucleophilic attack on the beta carbon, right? And we're going to call that atom number 1. And then after you form the enolate, right, if you count 1, 2, 3, 4, then the hydrogen gets added to atom 4. And that's why we call it 1,4 addition. Okay, 1,4 addition. Or you can call it conjugate, I'll just put CONJ period, conjugate addition. Either one is totally fine. So, like I said, the enol undergoes tautomerization to give you an aldehyde. So it looks like it's a 1, 2, but you guys know that it's actually a 1, 2, 3, 4. Give me a thumbs up if you're with me on that. It's actually a 1, 4. I know it looks like a 1, 2, but you guys know what tautomerization is by now. I don't have to teach that to you. So there you go. So all I've really shown you so far is the only thing that can do, or the only thing I've showed you so far that could do a conjugate addition is a cuprate. Okay. Well, there are other nucleophiles that we can use to do a conjugate addition. So check it out. This is kind of Dr. Klein's summary of it. So follow along with me. He says, starting at the top, stronger nucleophiles, that would be like a Grignard, tend towards 1,2 addition, whereas less reactive nucleophiles tend towards conjugate addition. So if you use an enolate, how many times have we talked about enolates in this chapter? I don't know, maybe 100 times or more. Enolates actually give you a mixture of 1, 2, and 1, 4 products. I would just look, your own instructor will write this down for you. Not very useful, okay? I'll just put here, not useful. I don't want to do a reaction where I get a mixture. That doesn't sound exciting to me whatsoever. But you guys remember a stabilized enolate? Like if you have a 1,3 dicarbonyl, right? 1,3 dicarbonyl. Well, the 1,3 dicarbonyl gives you a stabilized enolate, and then it does the 1,4 addition. So it actually does the nucleophilic attack here like this. So you actually get 1,4 addition, which we can also call conjugate addition. Okay, they both mean the exact same thing. And so what do? You can see this aldehyde, if you count the carbons starting at the beta carbon, 1, 2, 3, like this, you end up adding 1, 2, 3, and then of course the fourth carbon is that, this one over here, okay? But anyhow, so there you go. So that's conjugate addition. But again, what are they telling you? Well, so far we've seen a cuprate and we've seen a stabilized enolate. So here's the overall process. You take your stabilized enolate, you treat it with potassium hydroxide, you end up with the anion. But the anion actually attacks the beta carbon. You protonate to form an enol, and then the enol tautomerizes to give you an aldehyde. 1,4 addition or conjugate addition, we also call that sometimes we call it Michael addition or the Michael reaction. All of these names I would say, are used by organic chemists. You'll hear somebody talk about a Michael reaction or the Michael addition or conjugate addition or 1,4 addition. They all mean the same thing. You can imagine if we have a lot of different names for the same reaction. The reason why is just to annoy students would be number one. I'm kidding. But I'd say that the reason why has been there's so much mountain of work been done on the Michael reaction. It's been investigated, just in a big way. So the nucleophile, we have a name for that. We call it the Michael donor, right? Because it's donating a pair of electrons. And then the alpha beta unsaturated ketone or aldehyde, we call that the Michael acceptor. So this would be this one here. I'll color code it. So this would be the Michael donor. That would be the nucleophile. And then this aldehyde here, this guy here, this would be the Michael acceptor. Okay, so Michael donor and Michael acceptor. All right, so what did I tell you so far? I showed you 1,3 dicarbonyls and cuprates. Okay, I said those make good Michael donors. Besides those, what else makes a good Michael donor? Basically any 1,3 dicarbonyl. So you see, this is a 1,3 dicarbonyl, this is a 1,3, and you're like, isn't that just ethyl acetoacetate? Yep. Isn't this just diethylmalonate? Yep. Okay, so those are good Michael donors. And then you see this one here. Well, you could draw a resonance structure here with this nitrile because the nitrile has 2 pi bonds. Also, if you have a nitro group, right, you know that a nitro group actually looks like this, or you have a positive and a negative here. So you could draw a resonance structure like this. I won't waste too much time on that, but those are all good Michael donors. Now, what makes a good Michael acceptor? If you look over here, pretty much any alpha beta unsaturated carbonyl, whether it's an aldehyde. Look, I mean, they got the whole gamut here. They got aldehyde, a ketone, ester, amide, and then the 2 at the bottom, right? What do they both have in common? The nitrile and the nitro is they both have pi bonds, right? There's a pi bond here, and there's a pi bond on the nitro, right? So you know. Anyhow, I won't draw the whole nitro, but you get the idea. So we have our Michael donor and our Michael acceptor. So by choosing the appropriate Michael donor and Michael acceptor, you can, you know, make different compounds. And if you're thinking, oh man, this is going to be tricky to try to connect the dots for Michael reaction, I would say, yeah, in a way, but it's actually not that bad once you get a chance to practice it. So what we're going to do for this conjugate addition is we're going to draw the whole mechanism, and then we'll take a look at a final product and see how we could make it using a conjugate addition or a Michael reaction, okay? So for the first step, do I really need to draw the mechanism for the first step? Probably not, because the first step is just going to be deprotonation, right? I have hydroxide, right, from my potassium hydroxide, which looks like this. I end up abstracting a proton, and I end up with the doubly stabilized enolate. Again, I probably didn't need to draw this for you, but whatever. It's a beautiful day outside. So the next thing we're going to do is we're going to do a nucleophilic attack on our Michael acceptor. So this is going to be our Michael donor. Okay, so let's draw the Michael acceptor, which is going to look something like this. All right, like that. So we have our nucleophile. It's going to attack like this, and let's draw what we end up with. So Mr. Dion's going to be very careful. Now that I said that, I'll probably make a mistake, but anyhow, so we end up with something that looks like this. So 1, 2, 3. There we go. So this is going to be our enolate, like that. There's our negative charge, and then we have our 6-membered ring out there like that. So there you go. So that's this again is going to be our Michael acceptor, and so that's our intermediate that we get. So what's the next step going to be? Is we're going to do a protonation. So we're going to have H3O plus like this. All right. So we're going to do a proton transfer like this. Okay. And then we're going to end up, maybe I could just copy and paste. No, that's not saving me any time. Let's see if I copy and paste this, if I can save any time at all. All right, so we're going to delete this and this and this and this and this. Okay, so then we protonate like that to give us the enol. And then after the tautomerization, so I'm not going to draw the mechanism of tautomerization. I'll just put here tautomerization, okay, because I'm kind of running out of space. So what's our final product going to look like? Okay, so let's draw our 1,3-dicarbonyl like this. Then we're going to have something that looks like this, and then our carbonyl is going to be here like this, and then we have our cyclohexyl group like that. So let me just count very carefully. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, looks good. Like that. All right. There we go. So that's the mechanism of a conjugate addition. Yeah, pretty handy. And I just wanted to point out that the way I counted this was 1, 2, 3, 4, 5, like that. So if you noticed, when you go over here, right, you end up with 1, 2, 3, 4, 5, the 2 carbonyls being separated by 5 atoms total. Okay, so now let's say you had this compound here, and it says using diethylmalonate as your starting material and any other reagents of your choice, show how you would prepare each of the following compounds. So diethylmalonate, if you've forgotten, is this compound, so diethyl malonate, and we know that we can make a Michael donor, right, by treating it with sodium methoxide, right? We'd end up with a Michael donor. But anyhow, how do you know that you need to use a Michael reaction for this to make this compound? I'll show you how you know. 1, 2, 3, 4, 5. When your carbonyls are 5 atoms apart, then that's probably how you're going to do the reaction. So what we're going to do is we're going to make the doubly stabilized enolate from the diethyl malonate, and then we need to figure out what our electrophile is going to be. All right, we need to figure out what our electrophile is going to be. So if this portion here, let me just circle it like this. If this portion comes from the diethyl malonate, all right, then that would mean that this portion would come from our alkyl halide, okay? Now hold on. Notice that I said alkyl halide. That actually would be a mistake. Now why would that be a mistake? You cannot use malonic ester synthesis in this case. Now, why would that not work? Let me show you, and I'm probably going to run out of space. But let's say you took this compound, okay, diethyl malonate, and then you said, okay, I'm going to treat it with sodium methoxide, and then I make the doubly stabilized enolate, and then I need to add the part that's in the red circle. Well, the part that's in the red circle would be this. So you'd have the CHEM dimethyl, then you have this, and then you have something that looks like that. And you say, that's going to be my electrophile. Is that going to work as an electrophile, what I have written there? Will that be a good electrophile? Meaning this compound. Is this a suitable electrophile for an SN2? No, absolutely not. So we'll put here, will not work in SN2, right? SN2. Okay, it's not going to work. It's going to be a complete failure. And so you cannot use the malonic ester synthesis. So what does that mean? It means you're going to have to do conjugate addition. Let me show you what I mean. If we start out with diethyl malonate, and then we treat it with sodium methoxide, so sodium methoxide, like this, okay, in that case, we're going to end up with the doubly stabilized enolate. This will be our Michael donor. Now, what if we use a Michael acceptor instead? Well, in that case, it would be something much more reasonable. It's going to look like this. That would be our Michael acceptor. So now we can get our nucleophilic attack like this, and then after, and it doesn't ask us to draw the whole mechanism, but once the whole thing is done, we're going to end up with, so after a few more curved arrows, we're going to end up with this. So we're going to do our conjugate addition, and we end up with something that looks like this. So we have our two methyl groups, and then we're going to have this guy looking like that. So now all we have to do is hit this with aqueous acid and heat it up. And so what are we going to end up with? We're going to end up with, I'll circle it, we're going to end up with all of this part here that's in green, right? The rest is going to be lost from the ester hydrolysis and the decarboxylation reaction. And so we're going to end up with our desired product. We're going to have something that looks like this with our CHEM dimethyl. And then we have 1, 2 carbons and our carboxyl group on the end like that. So again, malonic ester synthesis will not work. And we'll put here, I'll write it in blue, must use Michael reaction. Michael or Michael addition or conjugate addition, I'll just call it Michael reaction. Does that make sense to everybody why you have to use the Michael reaction in this specific case? Okay. All right. It's not simple, okay? It's not an easy chapter, but that's the idea, is that you can't use malonic ester synthesis. You have to choose Michael addition in this specific case. Okay. So now we're getting very close to the end of section or chapter 21. We literally have what, 2 reactions left. We have to cover the Stork enamine synthesis and Robinson annulation. So if you go back to the Michael addition, right, what did we always end up with? We ended up with some kind of 1, 2, 3, 4, 5 dicarbonyl. Okay, but I wouldn't say not the problem, but you probably noticed that you always have to have, some kind of stabilized enolate to do that. Okay, to do this reaction, and so that leaves out compounds like let's say you wanted to use cyclohexanone. Okay, and oops, that's not very pretty. Let's say you use cyclohexanone, and then you wanted to treat this with, sodium methoxide. Well, that's just going to do an aldol condensation reaction, so that's not going to work, right? So you can't make a 1,5 dicarbonyl. So I'll put 1,5 dicarbonyl. Okay, I'll put a big X over that because this just wouldn't work. So it turns out that a guy named Gilbert Stork, who was a brilliant organic chemist, I mean, one of the best, okay, came up, and I think he was at Columbia. Anyhow, Gilbert Stork, really bright guy. He came up with all kinds of cool stuff. But anyhow, he developed what's called the Stork enamine synthesis. So he said, okay, this reaction doesn't work, but I can find a workaround for it. And you guys remember enamines? Remember that? We covered it in the section or the chapter on aldehydes and ketones. We said you take a ketone or an aldehyde, and then you take a secondary amine, okay, catalytic amount of acid, and you remove water, and you end up with an enamine. Well, it turns out that if you make this enolate, like I said, it's going to give you some kind of aldol condensation. And either way, this is such a powerful electrophile that it's going to attack the carbonyl carbon like that. So it would not be a Michael donor. So this is not a Michael donor. But if you make the enamine, it is a Michael donor. So the enamine is a Michael donor. Now, if you're saying, why would this be a Michael donor? Well, keep in mind, there's a lone pair of electrons on this nitrogen. And here's how, look, like that, it behaves as a nucleophile. So it's not as strong a nucleophile. So it serves as a Michael donor. So enamines behave like an enolate, right? You have the negative charge in the same spot, but it's less nucleophilic. So it's not as strongly reactive. And so if you put it in the presence of an alpha beta unsaturated aldehyde like this per se, it's going to do what? It's going to attack at the beta carbon. Okay, so it's going to do a Michael addition. So is that cool or what? So check this out. So what he did is this. He said, okay, I'll make an enamine, and then I'll put it in the presence of some kind of alpha, beta, unsaturated, either way, Michael acceptor, okay? So then what happens, I'm sure that you could all draw the product of these two curved arrows, right? You end up with this. Now what's going to happen when you take this and you heat it with acid? You're going to protonate this to make the alcohol, so you get an enol. That's going to tautomerize to give you a ketone. And what do you know about iminium ions? When you hit an iminium ion with H3O plus, it's going to give you a ketone as well. So you end up hydrolyzing the whole dang thing. So it's two reactions in one. So you can even put here 2 in 1. You protonate the enolate to give you an enol. That tautomerizes to give you a ketone. And then you hydrolyze the iminium to give you a ketone. So you end up with a 1, 2, 3, 4, 5 dicarbonyl. And of course, you end up with your secondary amine recovered in the end like that. So that's the Stork enamine synthesis. So again, the purpose is this. So if you're like, why do I have to learn this? You just taught me Michael addition. Now why do I need to know using an enamine again? It's because this will not work. You cannot just make an enolate out of this and do a conjugate addition, a Michael reaction. It won't work. You have to make the enamine out of this first, okay? Once you've made the enamine, then that will serve as your nucleophile to do a Michael reaction. So if you're wondering about like what enamine should I make, because there's lots of secondary amines out there, I'm going to put here usually, and I looked this up in the solutions manual before, he usually uses this compound, CH32NH. So this is called dimethyl, you guessed it, dimethylamine. Okay, so he uses dimethylamine and a catalytic amount of acid and removal of water. Then once you form the enamine, so of course in this case you'd end up with the enamine, so you can get some practice drawing your enamine, which would look like that. Okay, then you do the Michael addition. Then you do the hydrolysis, and you end up with your 1,5-dicarbonyl compound like that. Again, to have the foresight to do this is pretty cool. It's a pretty remarkable thing. So another thing that you want to remember is that when you do the Michael addition, we'll put here carbon-carbon bond formed between carbon 2 and carbon 3. So you can see the bond is formed right here between carbon 2 and carbon 3. So if you're planning a storic enamine synthesis, count out the 5 carbons in between carbon 2 and carbon 3. That's where you're going to form your bond. And that will help you if you're asked a question like one of these maybe. Okay, so it says use a storic enamine synthesis to show how you might accomplish this one. So if we count out 1, 2, 3, 4, 5, we're going to form our bond between carbons 2 and 3 like this. Right, we know that this is not a good Michael donor, and we're making a 1,5-dicarbonyl, so we want to use the storic enamine synthesis. So what's the first step going to be? Is going to be to make the enamine. So we're going to use dimethylamine, a catalytic amount of acid, and then of course I'll just write here negative H2O, right? So that would give us the enamine, which is going to be this. I'll just draw it over here. They're not asking for the whole kit and caboodle here. But that would be the enamine that you would form in this case. Then what's our Michael acceptor going to be? Well, you can see it's all of this right here. So it's going to look like this, okay? So that's going to be our Michael acceptor. So we'll scribble that down too. So I'll put here step 2. It's going to be put our Michael acceptor in like that. In step 3, hydrolyze the whole dang thing with H3O plus like that. There you go. You're done. For the next one, it's in the exact same vein. Look, we have a 1, 2, 3, 4, 5 dicarbonyl. The bond is going to be formed between carbons 2 and 3. You can see that this 5-carbon chain here is this chain like this. They just rotated this bond, okay? So remember, this is a ketone, so it's going to be no good for a Michael reaction. We have to convert it into an enamine. And so step 1 is going to be dimethylamine, a catalytic amount of acid, removal of water. That's going to make our enamine. The enamine is going to look like this. So I'll just draw it the way they have it there, okay? Then what's our Michael acceptor going to be? Well, you can see the Michael acceptor is going to be all of this portion here. We're going to have this 6-membered ring. We got our carbonyl. We got our alpha beta unsaturated ketone. So step 2 is to use this compound. And then in step 3, what do? We treat it with aqueous acid. We protonate the enol, or the enolate to make an enol. It tautomerizes to give us the ketone, and then we hydrolyze the aminium ion. And that, my friends, is the storic enamine synthesis. All right. So the very last reaction that we learned in this whole chapter is called the Robinson annulation. And I think it's named after Sir Robert Robinson. So if he's a sir, wasn't he knighted, I guess? Anyhow, but Robinson annulation is literally nothing more than the combination of 2 reactions that we already learned, okay? So we've already covered Michael addition. We just went over that. And last class, I taught you the I just taught you aldol condensation, right? So all you do in a Robinson annulation is you make the enolate, the doubly stabilized enolate, like this. It acts as a nucleophile, son of a gun. It acts as a nucleophile, so you have nucleophilic attack like this. You form the enolate that gets protonated to give you the enol. It tautomerizes to give you the ketone. Then you make this enolate, and then this enolate is going to attack over here like this, and then you do the E1CB reaction, and you end up with your alpha beta unsaturated ketone like that. So that's the Robinson annulation reaction like this. However, a couple things that I would add is that this is just an intermediate formed along the way, because this entire reaction can all be done in one flask. All you need is sodium hydroxide and heat, and it will do the whole dang thing. NaOH and heat heat, and that will take you all the way from here to here, okay? So you don't need a bunch of different reagents, okay? It's just sodium hydroxide and heat. You do the Michael addition, then you do the aldol condensation, and you're done. Okay, so let me show you how you would come up with the reagent. So all it's asking you for is like this part here. Here are the two reagents, 1, 2. So you need a Michael donor and a Michael acceptor. And it's saying if you wanted to make this compound via a Robinson annulation, what is the Michael donor and what's the Michael acceptor? So I'll show you the way that I do it. Okay, this is how I figure it out. So I do something like this. So if this is the double bond, right? This is the double bond that's formed. Come on, pen. This is the double bond formed from the condensation reaction. So my first retrosynthesis is going to look like this. Okay, so I'm going to leave everything intact. Okay, and I'm going to count here. So 1, 2, 3, 4. So 1, 2, 3, 4, like that. I have this carbonyl here. Okay, and then I'm going to have a carbonyl here like this. Okay, so all I've done here is I've just broken this bond. I put this as a methyl group, right? This methyl group right here. And then on the other carbon, I put an oxygen to make an aldehyde. So if you look at this, if we try to draw a little bit prettier, and I'm just redrawing the same compound, what it's going to look like is this. So you're going to end up with this compound. There we go. And then, oops, then we're going to have our methyl group over here. Then we have 1, 2, so 1, 2, 3, 4. So 1, 2, 3, 4. So there you go. So that's the first disconnection, okay? It's just for the double bond. So then the next part is going to be, if I count it here, 1, 2, 3, 4, 5, right? The disconnection is going to be between carbons 2 and 3, right? Because the last step was the aldol condensation. And then this step is going to be the Michael addition. So now we're going to do the retrosynthesis for the Michael addition or Michael reaction, doesn't matter, okay? So now what it's going to be is this. I'm going to have this 1,3 dialdehyde, okay, with a methyl group on here. And then that, I'm going to make my Michael donor from that. And then my Michael acceptor is just going to be this compound. So if I draw this here, like that. So those would be the starting materials that you would need to start out to do your Robinson annulation. Now, there's only so much yammering on I can do about how you do this. You have to try it yourself. So try, I'll put here, try this, okay? But hopefully the way that I showed you is going to be useful, okay? It's going to help you out in determining what the starting materials would be for a Robinson annulation. We're going to take a break in a second, but before we do, I just want to point out again that we've covered all of the reactions in this chapter. What's the trickiest thing about this chapter? It's about kind of determining where are the carbon-carbon bonds formed in here. And that's what I tried to relate to you when we looked at aldol reactions, whether it was an aldol addition or a condensation. Then we covered Claisen reactions. So those, remember, Claisen reaction, think of beta, keto, ester. And then when we looked at Michael reactions in the storic-enamine synthesis, we're talking about 1,5 dicarbonyls. And so you can kind of look at the positions of the functional groups to help you figure out how did they make this compound, right? If you see a 1,5 dicarbonyl, okay, that's a dead giveaway that it's going to be a Michael reaction or a storic-enamine synthesis to do that. If you see a 1,3, then if it's aldol addition, like this one here, right, that's a 1,3. If it's a beta keto ester, I think I've hammered that into your brain enough that you know that that's going to be a Claisen reaction. So you don't have to think about that one a lot. And so when it comes to alkylation, we learned a couple of different things. We learned that we can attack at the alpha position using an enolate. And we learned thermodynamic and kinetic, so we learned thermodynamic and kinetic way to do that. Then we talked about Michael donors and Michael acceptors in gory detail. So it says here you can also combine an alkylation with a Michael reaction. So let me just show you this. This is actually kind of cool that he even mentions this in the textbook. But all he's saying here is this. So All he's saying is give peace a chance. No, that's not what he's saying. Anyhow, so what he's doing is this: is let's say you have a cuprate. You know that a cuprate does conjugate addition, so it's going to add like this. Okay, so you're going to end up with this intermediate. Now I don't have a lot of room to draw, but you have your ethyl group here. Okay, then you're going to have your enolate like this. So then what happens when you come up with the methyl iodide? So you put methyl iodide. So now you're going to do this and you're going to alkylate. So you actually are combining alkylation with a Michael reaction kind of at the same time. And that way you can put something at the alpha. Come on, pen. Oh, shoot. Okay, you can put something at the alpha carbon and the beta carbon. So just be aware of this. This is a combination of two reactions that we've already covered in this chapter. So there you go. It's kind of a cool reaction. And so, what did we cover? Let's take a quick peek. So we covered alpha halogenation. Then we covered the Helmholtz-Zielinski reaction, the haloform reaction, one of the neatest reactions in all of organic chemistry, taking a methyl ketone and converting it into a carboxylic acid. All right, what's going on? Okay, anyhow. Then we covered aldol addition and aldol condensation. We said the difference was heat. We covered crossed aldol reactions. We covered the intermolecular aldol reaction. We covered the Claisen and the crossed Claisen and the cyclic Claisen, which is what we call the Dieckmann reaction. Then we covered kinetic and thermodynamic enolates and how to make those and how to alkylate. Today we covered malonic ester synthesis, acetoacetic ester synthesis, and what those are used for. We went over Michael reactions, which is this here stabilized carbon nucleophiles, which is just a fancy way of saying Michael additions or conjugate addition. Then we did the Stork reaction or Stork enamine synthesis. And again, you always want to be on the lookout for the old 1, 2, 3, 4, 5 dicarbonyl for that. And then the Robinson annulation, which is a combination of a Michael reaction followed by an aldol condensation. And that's the whole thing. So what we're going to do is there's 4 problems here. I think we deserve a break since I've been lecturing for about an hour. I think we deserve a break before we try these. But it says here, using cyclopentanone, which would be this compound here, in any starting material, propose an efficient synthesis for each of the following compounds. So I'm just going to try to guide you on the first one. Look, if you have a 1, 2, 3, 4, 5 dicarbonyl, and you're starting it with a ketone, that suggests that you have to use the Stork enamine synthesis, right? Because this is not going to give you a stabilized enolate. And so you need to make this bond right here, okay? You need to make that connection. And for the other one, this is something that's actually a little bit different, right? Because here we have a 1, 2, 3, and this is obviously not an aldol condensation reaction because we don't have a double bond here. This has something to do with an aldol addition reaction, but I want you to think about the enolate and how you could use the enolate as an electrophile to add this methyl group on here. Remember, one of the most powerful electrophiles you'll ever see is methyl iodide, okay? So that is very susceptible to nucleophilic attack. All right, I can't help myself. What are these ones about? Propose an efficient synthesis. So this one here, 21.45, is just getting you to practice this reaction. Come on, iPad. It's getting you to practice this. So it's 21.45. And then the very last one that I put on there was, this is kind of an interesting one. It's doing the same thing. So this is using that same concept, right? Because we want to put something at the alpha carbon and something at the beta carbon. Same thing here, alpha and beta. So it's a dialkylation followed by a reduction in that case. So during the break, I want you to give these the old college try, and then we'll come back and we'll tackle them together.